Hello, good afternoon. Do you hear me? Am I well? So I believe so. I should be. And how do I see what I'm sharing? So yeah, good afternoon, good morning, everyone. And I'm gladly to welcome you to, just give me 1 second. So yeah, hello again. My name is Nikolai Tushinsky from OneSpin Solutions. And I will be walking you through this today tutorial with the title Beyond Bug Hunting, with a deep dive into verification coverage, and also touch a bit on the certification, on the safety standards, and some advanced topics. So as I said, I'm with OneSpin. My name is Nikolai Tushinsky. I'm product specialist for design verification, and I've been working in the formal world for 5+ years, and yeah, that's about me. So this is my mail. So if you want to get in contact, feel free to reach me by mail. Before we jump into the presentation, I want to first introduce a bit what we at OneSpin are focusing on. So OneSpin is a team of that provides and certified IC integrity verification solutions to develop functionally correct, safe, secure, and trusted integrated circuits. And we focus on areas like functional correctness, safety, trust and security, targeting different verification flows from the design phase to integration and to implementation. On the today tutorial, I would like to bring you a bit of light what I'm going to talk about today. So first, I will touch on what are the verification flow challenges that we are solving with the OneSpin solutions. What is the coverage analysis, which is based on mutation from OneSpin, and this is called the OneSpin 360 quantify. Also on how the results from OneSpin can be integrated with results from simulation. This is done with the OneSpin 360 portable coverage, and in the end, we're gonna make a short summary, and we'll be open to answer the questions. So yeah, verification flow challenges. What are these? So let's visualize a classic verification loop. I believe that everyone is familiar with the verification loop depicted in this slide. So normally everything starts from requirements that are further on broke down in the verification plan that needs to be completed. Based on this verification plan, there are teams that are building simulation test benches and that are run in case there is failures. These are debugged, coverages being collected, and later on the metrics needs to be assessed. And after everything is green and all the sign-off criteria are done, when this is the moment we are ready to sign off. Of course, in our days, we are not having only simulation, so we are having formal technology which is available, and it's becoming very, very mature. And this is from a classic simulation verification flow, it brings us into a hybrid one. The same thing applies, so it's everything are starting from requirements, broken into verification plan, but now the teams need to plan for both, for simulation and formal. And later on, after the broken is performed, there are teams that are developing formal test benches, and there are teams who are developing simulation test benches. These are run in their own environment. So in formal environment and simulation environment, run, debug, of course, and then the coverage is collected. But there is an aspect that these technologies are kind of separate, and this needs to be assessed. So assessing the quality of the verification, mainly it's a good tool to do it, and we need to answer while we are doing the assessing of this quality of verification flow process. Ask the question. We need to answer the question: when are we done? So basically, if we need some sort of metrics in order to assess, and if we don't have this, then we don't know, and we are just can be redundant and so on. So answering the question, when are we done with our verification, there is not only one aspect to be taken into account. So basically, we need to answer a couple of questions. So in our case, what part of the design has been exercised by assertions and covers, because we are talking about formal verification here. Did I write good quality assertions? Of course. Which parts of the design have been checked by my assertions? And on the other hand, are all specified functions implemented and are all specified functions verified? So if the first three questions that are falling from the main question are more on the structural side, on the code coverage side, these are tackled and answered by Quantify, which is not the main topic, but it's a big topic of the today tutorial. And on the other hand, there are two more questions which are more on the specification side, and this is tackled with the one-spin gap-free verification, which is out of scope for this presentation. All right, so let's not focus on the first one. So Quantify targets two aspects. One is the coverage, and the other one is the bug hunting. Both are of tremendous importance, and of course, getting 100% coverage with bugs in a design is unacceptable, but this can happen, of course. If we are not careful and if we don't do our due diligence, then we can end up with bugs, even if we're getting 100% coverage. On the other side, extracting coverage should be quick and easy. So especially when it comes to setup times and these kind of steps, phases, when this extracting coverage from the test benches that are run shouldn't take much time and should be easy. And also, when we are collecting this coverage, the report that we are getting or the report that we are putting together, this report should contain meaningful data. So what are the problems with the current formal coverage solutions that are existing or existing? These are more inconclusive. So let's list a couple of them. So we know about the cone of influence, we know about the proof core, and let's take it one by one, and let's see what they are bringing into the picture. So the cone of influence, this is very old and well known. It's mainly for an assertion. It's getting all the signals, and it's in our case in this picture it's the triangle, and it's very over optimistic. Even if its signals are in the cone of influence, some of them are much logic of it is not relevant for the assertion proof, which gets proven. Also, the proof engines try to trim irrelevant logic. On the other side, we have a proof core, and proof core is also over optimistic, and it's engine dependent. The results are hard to interpret, need support from vendor, mismatch with abstraction level of other forms of coverage, and the review is becoming a tedious process. How we tackle this, so how we make sure we are not getting inconclusive formal coverage results, we have using, and let me introduce the technology that is under the hood of the Quantify, and it's the mutation-based coverage analysis. What is mutation coverage analysis, it's a multidimensional view over the coverage. So, and the mutation based is actually answering two main questions. Is my location in being activated or controlled? And is my location being detected or observed? So mainly shortened questions would be like, okay, been there, done that. So in the first case, when we talk about activation, this is equivalent to a simulation hit. And the idea, so if a statement is not activated during the hit verification, it's not hit, it can't break a check, of course. If a statement has been reached or activated, would a check fail? So this measures the quality of the stimuli. On the other hand, we have the detection or observation aspect, where the idea is that if this is a follow-up from the activation, so first a statement needs to be activated in order to be detected, and if a statement that has been activated is modified, of course, this is similar like to introduce a bug. And the question is, does at least one check, in our case assertion, should fail? And this measures the quality of the checkers. This measures on how good are your assertions. So yeah, mutation coverage, multidimensional view, and it talks about quantity and quality. It assesses the quality of verification by providing a quantitative metric. And the quantity is the structural coverage. So its activation and detection coverage provides quantitative assessment. And on the other side, the mutation coverage provides the quality by function, meaning of functional coverage, where the assertion coverage provides the qualitative assessment of it. So yeah, we incorporated the mutation-based analysis in OneSpin 360 Quantify, which is the solution for coverage analysis from OneSpin. The solution itself is, I will touch and bring a bit of light on four main aspects that are of interest. One are the metrics, precision, the usage, the return on investment, and the confidence for sign-off. So the current solutions that from the metrics point of view, the common simulation metrics are not always adequate, so only measures the control coverage, so the activation side. Observation coverage is done in terms of cone of influence. General mutation coverage is too slow. And one aspect of the metrics that we also tackle with another solution that is playing together with Quantify are the different environments or different formats in which the results from simulation and formal are represented, and how we close the gap by making this integration between these two types of results possible. The usage, on the usage side, yeah, so integrating separate solutions is time consuming. There is no common interface to easily interpret results. Low ROI, so verification quality is lacking, metrics are not focused, requires separate licensing and installation, etc. And on the confidence side, it's time consuming, and it leaves undetected bugs in simulation. So verification constraints and conditions still a mystery. How we Quantify understand this and manages to outclass and get rid of these. I mean, to make the most out of this. So on the precision side, so Quantify is providing accurate and reproducible results by mutation analysis. It's fast, so the execution runtime is fast by the mutation being applied on model-based, and does a precise mapping to source code by source location tracking. Easy to use, it's a push-button solution, so once the formal test bench has been developed, there is no much that can be done to run the coverage analysis. On the ROI side, so it comes together with the assertion checker, so there is nothing on top of it. More interesting is on the signoff side, where this Quantify provides a reliable identification of verification gaps and blind spots. It's highlighting the over-constrained, dead, and redundant code, and the results that are computed from Quantify can be integrated with third-party verification planning and tracking tools. All right, so now that we listed what are the advantages of Quantify, I would like to get into how this looks. So I will touch on two aspects. One is the activation coverage, and when we talk about activation, there are two aspects that are very strongly formal. It's the possibility of the formal to identify the dead code, and also the possibility to identify the over-constraining. The dead code is something that is introduced by designer in the RTL, so and the mutation cannot be activated. On the constraint is when the verification engineer is putting obviously some constraints on the interfaces, and these constraints are leading to some dead code. And the Quantify is making the difference between these two types of coverage. Of course, they are kind of in the same bucket. So dead and constraint is just the source of the dead is coming from different. The source is different. Now on the detection side, so how we do the analysis, so how we classify the metrics. So we assess the quality of the assertions in tools. So the quality of the assertions by highlighting the source and applying this mutation analysis, and the results can have a two outcome. One is the covered and undetected. So mainly covered means that after mutation has been performed, at least one check is failing. And on the other side, the undetected, which is the opposite of the covered. So if a mutation has been applied, there is no change in the results of the checkers. There is also additional some coverage results that are being reported on top of it. So these are the formal is good in identifying redundant code as well. So this is mainly the code that doesn't contribute to the designer IOs. And verification and excluded by user code is actually not part of the matrix itself. So this type of code is classified under the different category. So how I already mentioned that running Quantify does the source annotation. So usually when you are running thirst without having any assertions, without having any dead code, what you are getting is such a nicely Christmas red source view annotated, meaning that, okay, you don't have any checkers, there is no dead code, and you should write some assertions first before applying. Once you're writing assertions and you are doing verification, you are ending up having such a dashboard where the results are reported, and this is you can see that you're having the colors, and also you have the sources, etc. So, and you're getting some metrics. The most important side is that you are getting the absolute metrics, relative metrics, what assertions are part of this, and your goal in the end is to reach such a green side, green view of the source code. Once you are getting such a green, meaning that, of course, with your assertion test bench, you are covering most of this, most of the locations in your RTL. This is the example is from a previous tutorial that we dived deep, I think it was in DVCon US 2018, where we show on how exactly step by step is to achieve 100% coverage with no over constraints, no design bugs, and being ready to sign off. But how is also the quantify can be used not only by verification engineers for sign off, but also to be used by designers and verification engineers for iterative sign off. So basically, of course, in some there is the verification flow, it's an iterative process. So every time there is a change, so you have milestones that needs to be reached. So this is very good to be used by designers when designing, and also by verification engineers while they are developing the test bench. When you're developing the test bench and you are writing some assertions, you are getting an immediate feedback on how good test bench assertions have you written, and are you on the track of doing the right thing. Now let's dive a bit deeper and get a bit of taste on how quantify and the mutation-based coverage analysis as a technology can help you get most in the standard landscape. So OneSpin is being active across many safety standards. So we are talking about the functional safety standards. We have the DO 254 on one side, which is the aerospace defense, and then we have the IEC standard, which incorporates the automotive. I'm talking here about the 61508, which incorporates the automotive, which is kind of closer to our heart, but this doesn't put a limitation on the others, like the process control, nuclear, railway, and as well. Excuse me. And when we talk about standard, we're talking about mostly of the requirement tracing and proof of evidence that we are doing the right thing. And this tracing and coverage metrics are playing together, and they are actually playing a paramount importance. Remember the verification loop we had? So this is a derivative with more focus on the planning. So of course, everything starts from requirements, then you have an implementation plan that goes into verification plan, and this verification plan will have requirements that have features, sub-features, verification goals, and then you need to decide on what is your technology that you're gonna tackle this aspect. And how a DO 254 development flow overview looks. So this is the courtesy of PCA. And if we look closer on the process, I believe we have the planning side, the requirements here, the verification process here as well, and the question on how can formal verification make this flow more rigorous. And when we say make this flow more rigorous, we talk about how can the functional metrics and the coverage metrics help in to get this flow rigorous. And the first step would be to do design code analysis and to make sure that the correct RTL is served upfront. Of course, from RTL, there is synthesis, place and route, and then it ends up on the physical device. but we start at the early phase during the RTL design. What we do during the RTL design, we do requirement tracing and verification, and code coverage closure for simulation, and code coverage for elemental analysis. As you know, as I pointed out already, so formal is very good at getting the dead code issues and running formal reachability analysis. You get an immediate feedback of the dead code issues. And here is an example of it. So for a quantitative analysis of simulation completeness in DO254. So the problem here is that insufficient code coverage during DO254 element analysis prevents certification. For example, taking this branch, it will be never executed because the acknowledge cannot be asserted in this context. And the solution would be that you are running formal inspection using DV inspect, which is a pre-step to the to the quantifying coverage analysis, but the dead code is also transported into the covered solutions. But as a first step is you are getting quick feedback and of that this is dead, and such that you will not get stuck by preventing the certification. You can document the proven dead code, or if there is there's no reason why this is dead, of course this needs to be fixed in order to achieve certification. On the other side, we have the let's say another example is the FSM state and transition coverage. And OneSpin has the possibility, the formal has the possibility to find and extract FSMs from RTL automatically, checks coverage for all FSMs, states and transition in DET, reports number of cycles from reset to reach a state, from reset to reach a state transition, and reports state transition that cannot be observed. This ends up into a nicely matrix view of the pair states and the transitions, such that makes the analysis much easier. But why I'm talking to you about dead code and FSM is actually because in code coverage for elemental analysis in the DO254 verification flows, this is coming from the design assurance level AB, which are governed by DO254 Appendix B. And this says that there are several methods, including element analysis, and one of it is code coverage to ensure all design code is exercised. So what we have here, we have statement coverage, and this needs to get all statements to get executed. Then we have a branch coverage, all branches reached, FSM coverage, all states and transition reached, toggle coverage, no signals get stuck, condition coverage, and focused expression coverage. OneSpin targets all of these items. So statement coverage, branch coverage is targeted with quantify. FSM coverage, toggle coverage is targeted with the specific apps. Condition coverage and focus can be targeted with the assertion-based verification. Alrighty, on top of that, we provide the so-called tool qualification kit that makes the process of certification much easier. And this comes in terms of tool qualification guidelines, testing packages, and other elements. There is touching also on the other side of the standard. So we have the IEC 6150, and I will focus on the automotive side here. So in the automotive ISO 262, we have processors, DSPs, hardware safety mechanisms, and many applications that require safety measures to be taken, and this includes requirement tracing, hard soft error detection and control, And there is plenty of documentation that you can read through this from the links attached to this presentation, where one's been helped to verify automotive specific designs. Automotive is not an exception, so it's the same flow, requirement specification, broken down into implementation plan and verification plan, and based on these, the requirements are broken in features and sub-features, and for each sub-feature, verification goals that are tackled with different technologies. There is no difference in the use model, and for that reason, the tool qualification kit for ISO 26262 is provided by OneSpin, which we pass the tool suite audit and factory inspection. And the tool qualification comes with a defect management, bug notification system, documentation safety manual, safety certificate, and reports. And they are ready to apply for the TCL3 and the ISO 26262. So OneSpin 360 DV is when to use it during the RTL development, assess the quality of COTC IPs or legacy modules, and also when to use it is for code coverage closure for elemental analysis when we go into the DO254. The benefits of using it for is to get rid of the corner case bugs in the design as soon as possible. It comes with low noise with an intuitive debug environment. It's robust and efficient analysis of code coverage holes. You've seen the annotated source view, and it does a tool assessment, so independent assessment for review of results. On the certification side, so it's consideration on potential strategy and benefits. So when it comes to certification, nobody specifies you how to specific to do it, but it can be done with the tool assessment. So basically independent assessment through overlapping methods, remaining gate-level simulations and onboard testing, or through verification credits. All right, so now that we are getting the results, we kind of know what is required to get certification and all this kind of stuff. What do we do with these coverage results that we are getting from OneSpin? And in terms of coverage results, we are talking here about the code coverage and also about the functional coverage in terms of assertion results and cover properties. Yeah, so let's go and see what is the integration problem. So in the previous hybrid verification flow, we had some missing pieces. So we have that the verification plan that is being developed for both formal and simulation needs to be annotated now. And this is actually one document and needs to get information from different tools, which in most cases it's kind of not really possible. For that reason, we have this missing piece. On the other side, we have the measure of assertion quality. This we do with the quantify. Then we don't want simulation to spend time on the dead code, the identified and validated locations. So we need a way to communicate to the simulator, not to spend time on what is dead. And on the other side, what we have is we need to integrate this simulation formal coverage into one database that is later used to annotate the formal verification plan. All right, so let's see how we solve this problem with the pieces. This is solved with the OneSpin 360 portable coverage solution that solves several challenges. But before I go into the challenges that are being solved, just bringing you a bit on the overall flow on how is the open integration is happening. So you're again everything starts from design specification, ends up in some verification plan, tool, or spreadsheet. It doesn't really make a difference. And we have a DUT, which is common for both technologies. So this verification plan incorporates the formal and the simulation part. So someone decided that we are doing this block with formal and this block with simulation. And then we run some simulation on the interconnect side, and we verify some interfaces with the formal. And the test benches are being developed by the same team, by different teams, actually also doesn't matter. Okay, now, before we run any simulations, okay, I would say that let's get the dead code and report it to the simulation. This is the branch that talks about getting what is dead and validated in formal and communicate to simulation, and then run the simulation. This will save the runtime and also the effort to try to specify to hit some locations that are in fact dead. On the other side, we have the formal, which are running through the property checker, and then there is coverage solutions. The coverage solution is run, quantify is run on top of it. What we get? We get coverage, and we get functional results. Functional results are passed through the VPI, which I'll introduce shortly later in this tutorial. So we have the proof results passing through the app, verification planning integration app, and the results are being annotated back into verification planner. When we talk about coverage, the results are passed through another app, which is part of the portable coverage solution. And this portable coverage solution, so is the VCI app, is verification coverage integration app, ends up in the coverage viewer. Note that the loop is closing from both sides, from simulation and from coverage, and from formal, from mutation-based analysis tool, into one common view, and the test results of the simulation and the formal assertion results are getting into the same verification planner. So let's break down app by app in the portable coverage solution, and first in the row is the coverage closure accelerator. So as I pointed out, formal identifies dead code in no time. And this dead code is found to be unreachable, and the coverage closure will provide this information to the other tools in the flow. So what such that the verification team will know not to waste time trying to hit unreachable targets, saves many simulation cycles, and accelerates the coverage closure. So in the graph I have here, so we can see the blue trend is actually using UVM, and the red trend is using UVM with coverage closure accelerator app. So there is the trend is much steeper in terms of UVA, and the coverage the coverage metric is higher when used both UVM in combination with the CCA. How does it work? So you have the design, then you have simulation test bench being developed. The dead code analysis is run, then the reachability formal analysis database is calling the CCA app, which ends up in coverage waivers that are later on fed to the simulation environment. And this is boosting up the coverage metrics, which in fact, if you wouldn't use dead code analysis, then you will try to hit something that is dead. You don't know that is dead, and you waste a decent amount of time to identify that something is dead. And why not making use of the dead code analysis from formal? The next in the row is the verification coverage integration app, and this is the app that is solving the problem, the code coverage problem. So what is the app doing is gets the quantify results and generates the same results. I mean, generates the coverage, the same coverage reported in a third-party database that can be used together with our simulator. So it enables the integration of coverage from simulation and formal, and it's part of the OneSpin portable coverage solution. So because because Quantify is mutation based and simulation is only activation side, it's we encourage you to do first side-by-side analysis before merging the results. Once you did the analysis and then you're having for each location at least each location to be covered by at least one technology, then you're safe to merge. And yeah, so it's because Quantify mutation-based analysis is much stronger, it might overwrite the hit simulation coverage. So just to be safe, we encourage to do side-by-side analysis, because these are two sources of metrics, and after you pass and you make sure that everything is covered at least by one technology, then you can safely merge and generate the report. This is, I believe, it's can be done very automatically, so shouldn't be a problem. How does this get results? So basically, what is reported in Quantify to be covered. So you can see that you have red and orange. Orange is actually covered, is actually red now because we did a simplification of the metrics. So red becomes red, everything is excluded. On the functional coverage side, so we have the verification planning integration, which is the next one, and it takes care of getting the OneSpin results, assertions, and covers into a database that can annotate the verification plan. So this works perfectly with any verification planner and enables integration of results from simulation and formal. It is part of the OneSpin's portable coverage solution. And in this example, we have a verification plan that is developed both for formal and for simulation, including the structural coverage. We developed assertions, prove them with a property checker in OneSpin, run them through the VPI app. In the end, we get a database that we use to annotate and get such a views in our verification planner. The rest, which is red, needs to be either covered with simulation, or we need to put more effort in order to cover it with formal. Taking an example, a real example. So this is how the integration works with Questa. So we have such a verification plan. So you can see that we have a formal verification on the lower side. Then we have some cross checks, some code coverage here, some cover groups, and everything placed together. You can see that what we specified in this verification plan is being reported successfully in our Questa verification report. And yeah, also with VCS, this works without any problem. So you can see that the same applies here. So we get the coverage here on the bottom, and then we get the cover groups and the coverage metrics, the code coverage here annotated. So there is actually also no problem here at all. And again, bringing the overview. So what we have it starting from design specification. Then we're having a verification plan that needs to be annotated, and the coverage viewer where we need to collect the metrics. We start from DVT, where someone broke down what parts of the DVT we need to target with simulation, what parts we need to target with formal. First step, we run CCA app, the coverage closure accelerator app that gets the dead code being reported in waivers that are fed in to the simulator calls. And simulator knows that these locations are formally dead, proven to be dead by formal technology, and it doesn't spend time on trying to hit it. On the other side, the assertions are being proven, so we get hold with a reachable witness. We do coverage analysis, and then we have mutation coverage, the coverage database, the code coverage from reported by quantify, and then we have the proof results, the assertion results. We are running them through the verification planning integration app that ends up generating a database that is used to annotate verification planner. And on the other side, we are having the verification coverage integration app that is generating and makes possible to get quantified coverage to view in a third-party verification coverage view. So this works together with a simulator. So simulation coverage works with foundation coverage into one view, functional coverage, and the assertion coverage from one spin into the same verification planner. Summing it up, so what challenges we are solving? So we integrate formal and simulation coverage. We accelerate the coverage closure. We track formal results in verification planner. Everything is part of a portable coverage solution. You can use it with any simulator and planning tool. And yeah, of course, simulation verification is optional, so it works perfectly without simulation. And formal verification, the coverage, model-based mutation coverage is quantified. Then we are having the three apps that are part of the portable coverage, the verification coverage integration app, which talks about the code coverage, coverage closure accelerator, which takes the dead code results and gets them, helps to do a faster coverage closure, and the verification planning integration app, which is the guy that gets the functional coverage into verification plan being annotated. So yeah, summing up the entire story. So the coverage solution from one spin can be used by designers with the terms of the automated check. So it's a designer bring up. So you have reachability analysis, finds design bugs as you bring up the design redundant code. Also, the designer asserts the things that are embedded in RTL, they get taken into account and get coverage when you have designer asserts. On the functional side, so we have the verification quality and metrics. This is a must-have tool for if you don't want to have gaps in verification and show, and this is helping you with pointing out where these gaps are, identifying missing or low quality assertions. This is very important. Also, the over-constraining, which is a big problem for formal verification engineers. So because there is no such, there is not a lot of control on, and you need a bit of expertise on to get the constraints right. So basically, there is this concept of assumed guarantee, which is always taken into account. But also on top of that, you are getting quantify that can highlight parts of the design that are being over-constrained by your interface constraints. The most important, it's a push button. So once you develop your assertions, you don't need to set up fancy environments. It's a push button solution that generates the report. Once you get the results, you're having the quantified coverage collected, you have the assertion results, and also the dead code there. What do you do with them? You make use of the portable coverage, which helps to integrate formal and simulation coverage. This accelerates the coverage closure, tracks formal coverage results into verification plan, and you can use any simulator and verification planning tool. With the standards, when it comes to functional safety standards, this is very challenging. we have proof, and also we are working towards this direction of making the most of it. So we are well aware that requirement tracing is crucial, and the coverage is one considered evidence of for the safety standards. But so basically, coverage is taken into account and is considered one of the evidence that you're doing a good verification. And yeah, OneSpin provides high quality tool qualification kits for multiple safety standards that if you're in this area, just get in touch with us so we can work on this together. So as I pointed out, there are references and further reading that you can access through our website or through the previous conferences. We have like topics for formal safety verification, qualification metrics for formal property checking, and some other interesting stuff that if you are interested, feel free to look at it. Again, what are we OneSpin and what is our focus? So our focus is to provide IC integrity verification solutions to develop functional, correct, safe, secure, and trusted integrated circuits. Focus on functional correctness, again, safety, trust, and security throughout all the phases in the verification flow: design, integration, and implementation. On this note, I would like to thank you everyone who took the time and attended this short tutorial. More will come in the future, of course. If you have questions, feel free to get in touch with me by mail. And yeah, looking forward to talk to you soon. Thank you very much.